Howdy, everyone. Happy Wednesday. I hope your semester is going well. Please note that your first problem set is due Friday. I think our intent was if you can load it onto eCampus, that's the best way. But I'll check with the graders about it, and then I'll send everybody an email about how to submit it. And you have until midnight Friday to submit that. Okay, so last time we talked a little bit about Heisenberg. The gist of Heisenberg's uh, uncertainty principle is that we now realize that things like electrons and protons are not only particles, but they also have wave properties. And if you think about a wave, you can't have a wave if you have just one point. So you can't possibly know where something is. And what I pointed out last time was if you had a freely flying electron according to the de Broglie relationship, and you knew exactly uh, what its position was, or what its, let's say if you knew exactly what its velocity was, then you would know what its wavelength was, but you would know nothing about the position because the wave would start at minus infinity and end at plus infinity. I never met Heisenberg, uh, but here's a terrible picture, and I want to apologize for this, but this is a copy I made from an old transparency that I had that I took out of a book that the Humboldt Foundation in Germany gave to me some years ago. So this is a picture in October of 1973. All you can see is the silhouette of Heisenberg right here. And he was president of the Humboldt Foundation in Germany, which is the leading research foundation in Germany. As it turns out, about 5.5 years after this, the Humboldt Foundation gave me a very nice award called the U.S. Senior Scientist Award. I kind of smile at the name now because that was 30, 40 years ago. And if I was a senior scientist then, I'm not sure exactly what I am now. In any case, when I received the award, I received it from the president of the Humboldt Foundation, who no longer was Heisenberg, but was another Nobel laureate named Lunin, who was a biochemist. But my association indirectly to Heisenberg is through Heinrich Pfeiffer here. He is the uncle of the movie star Michelle Pfeiffer. You can see here he's a secretary general of the Humboldt Foundation where Heisenberg was the president. I got to know him really well because of my award. I wound up spending a year in Germany, and so we got to be pretty good friends. And to jump forward a long time, something like 10, 12 years ago, I got elected to be president of the Alexander von Humboldt Association of America, which was a group of American scientists who had collaborations with Germany. So I sort of indirectly knew Heisenberg, but that's pretty much the best I can do with that. Okay, so we finished talking about Heisenberg, and then we went on and I reminded you about translational motions. Then we talked about the harmonic oscillator, and we saw that we could figure out what all the harmonic oscillator wave functions would look like. They're given by this formula, which has Hermite polynomials. The Hermite polynomials can be obtained if you know the first two by what's called a recursion relationship. And here's an example of how putting the first two together work. I also wanted to point out for the harmonic oscillator, when you apply the model to molecular vibrations, then you can see where you get the kinds of frequencies you saw in infrared spectroscopy when you took organic lab. So if you take a hydrogen atom and you hook it onto something heavy, like a large organic molecule, we can think of this as a simple one atom vibrating against the rest of the molecule. A carbon-hydrogen bond is about 5 millidynes per angstrom, as I've indicated here. The range of force constants in general are about 1 to 20 millidynes per angstrom. So those are the units we typically like to use. If I remember correctly, there are 10 to the 7th dynes per Newton. It might be 10 to the 5th. I'd have to check my math. Your book will use units of Newtons per meter, which range from about 100 to 2,000. Spectroscopists don't like the Newtons per meter because bond distances typically vibrate on the order of 1/10 of an angstrom. So it makes a lot more sense to use units of millidynes so you can actually have real value of how much energy has changed. But let's do a sample calculation using the formula that I've given you before. Vibrational frequency is 1 over 2 pi times the square root of k over m. We need to know what m is, and so we'll do this for the hydrogen atom hooked onto something heavy. Its mass is 1 atomic unit. If you want to get from atomic units to grams, you divide by Avogadro's number. So this is something you will need to know, maybe not for the first exam, but later in the course. Make sure you can convert from atomic units into grams. So anyway, this is roughly the weight of a hydrogen atom in grams, 1.67 times 10 to the minus 24. That's what we stick into this equation. This 5 times 10 to the 5th grams seconds to the minus 2. This is the same as having dynes per centimeter instead of having millidynes per angstrom. And you see we get a frequency of about 8.7 times 10 to the 13th. I think I told you last time, expect vibrational frequencies to be roughly 10 to the 14th, maybe drop down to 10 to the 13th. Now, this is not the unit that you would have used in organic lab for infrared spectroscopy. You would have used wave numbers, or which are reciprocal centimeters, and the conversion between seconds to the minus 1 to wave numbers is you divide by the speed of light, and here we get 2910, which is typical of what you have for a carbon-hydrogen stretching frequency for organic molecules. And we have a chat question. Someone wants me to zoom in a bit. We can do that. Hopefully that's enough. I don't want to get to small fractions of pages. Okay, that seems to be enough for whoever needed it. All right, so that's just an example of what I wanted to show you about the harmonic oscillator and how it relates to infrared and vibrational spectroscopy that we're going to talk about later. So this 2910 fits into the range of typical carbon-hydrogen stretching frequencies in organic molecules, and they're about 2850 to 3100 wave numbers. Many industrial labs, including Dow, where I have 6 or 7 of my students working there, do a lot of analysis of their materials by infrared or Raman spectroscopy. And so it's useful to know what kind of magnitudes you expect for various kinds of frequencies. Someone asks what a wave number is. A wave number, if you look at it, it's reciprocal centimeters. So to be exact, it is the reciprocal of the wavelength of light involved. But why we use centimeters to the minus 1, it's a very useful unit because vibrational frequencies wind up all being between 0 and 4,000 wave numbers, or more likely even 50 and 3,500, 3,600 wave numbers that you have, but it's a reciprocal wave length. Okay, last topic we want to cover in the general area of quantum mechanics, and specifically under energies of motion, involves rotational motion. Later on, we will talk about rotations of diatomic molecules and even polyatomic molecules. We'll also go to talking about electrons rotating around nuclei. And so we're going to want to look at some quantum mechanical results that come out of this. But I want to start and look at a hypothetical problem. And we will first solve it by common sense and the de Broglie relationship. And then I want to show you that we're going to get the same answer with a Schrodinger equation. So for that reason, I like this problem quite a lot. Now, this won't be a realistic problem. A true rotation is going to involve 3 dimensions. And we're going to simplify our problem to 2 dimensions. After we do the 2-dimensional problem, I will go and give you some results for the 3-dimensional case. But here's your model. As you can see, it's very artificial. We're going to stick a particle, like an electron, into a plane. Think of it as an XY plane or an R theta plane. And we're going to fix the distance that this particle is from the center of a circle, and we'll have the particle going around in a circle just like this. Okay, so fixed R, fixed circle, and 2-dimensional plane. Momentum, as always, is mass times velocity. De Broglie here we're going to use, as we have before, lambda is equal to Planck's constant over the momentum. I don't think I've mentioned angular momentum before, but you'll remember from physics, angular momentum is linear momentum times r, the distance to the center of the circle. So it comes out to be mass times velocity times radius. Kinetic energy, I've written it several times before as p squared over 2m. If you look at this relationship, you'll see that we can then write it in terms of J. The relationship from J to P is that P is equal to J over R. So we'll plug that in, we get an R squared in the denominator by doing that. Hopefully you remember from physics the moment of inertia formula, but if you don't, it's okay too. Here it is. Moment of inertia of something going around like this is mass times the radius squared. We're going to have a situation with 0 potential energy. And so our total energy is going to be kinetic energy. It'll be J squared over 2I. So I'm substituting the I into the denominator here. Okay, I'm going to skip the next page for now. And actually, I maybe should have started with that, but let's do this specific problem first. Okay, so we have this particle going around the circle, and remember that the particle knows it's also a wave. So if the wave is going around the circle, as you learn from physics, when waves combine, they can combine constructively or destructively in order for the wave not to destroy itself. When it gets all the way around the circle, it has to connect up correctly. So picture starting at this black dot, we go around here with a whole bunch of waves, and at the end point has to match up from where we started. And what we will now see is that this is going to quantize the momentum, the angular momentum, and ultimately the total energy. Someone asks about the potential energy. As I said, we will be using there is 0 potential energy acting on the system. Again, it's an artificial system. We're forcing it to go around the circle, but we're not going to have any potential energy. Okay, well, we all know from way back from sophomore high school, if not before, the circumference of a circle is 2 pi r. In fact, if you've ever wondered why 2 pi radians is going all the way around a circle, that's where the relationship comes from. It relates the radius to the circumference of a circle. Anyway, it's 2 pi r. And as I've shown you in this picture and explained, we have to have an integer number of waves. So we will say 2 pi r, the circumference has to be equal to an integer number times the wavelength. And in this case, it can be 0, 1, 2, 3, 4, 5, etc. We allow 0, and what we're going to see is 0 is going to give us no rotation. So we won't create a wave if n is 0, and we will not have any rotational energy. If we go to any higher value of n, 1, 2, or 3, we will have rotation, generate some waves, and create some or have some energy for the system. Okay, well, this quickly gives us a formula for the wavelength. It's going to have to be the circumference divided by an integer. And we know from de Broglie, the momentum is h over lambda. We plug in for lambda. It's in the denominator, so we put a 2 pi r here and up there. And since we have h over 2 pi, we can write this as h bar. So the momentum has to be nh bar over r. And the angular momentum, which is momentum times r, is nh bar. So we have quantized the momentum, we've quantized the angular momentum. And from the previous page, I had this formula for the energy. And so since we know what J is, we can write that the energy levels will be n squared h bar squared over 2I, and n can be 0, 1, 2, 3, 4, etc. So these are the possible energies that we can have. And this includes 0 energy that we can have for rotation. Haji Ali raised her hand. Do you have a question?
Yes.
Okay.
My question is, so when you're saying that we've quantized something, like how we just quantized angular momentum, is it because of that h bar term?
It's because it goes ultimately back to the fact that we have wave properties, and you can think of this as a boundary condition. The wave has to match up on itself, and that dictates why we can only have certain specific energies. So this 2 pi r equal n lambda, that's basically our boundary condition that we have for this particular problem.
Okay, thank you.
Okay, so as I said, if we said n equal to 0, that means no rotational motion, no rotational energy. Higher n means more waves, higher curvature, and I've now been beating this into your head many times. The more waves you see, the more curvature you see, the higher kinetic energy we're going to have, and the faster motion it'll be. We'll have this silly little particle going faster and faster around the circle, but the faster it goes, the more waves it's going to generate. So hopefully this derivation is pretty clear, but I want to change the nomenclature just a little bit because I want to equate this to what you would have seen in freshman chemistry. You would have talked about quantum number m sub L for this kind of effect rather than quantum number n. So let me point out that by implication, I was assuming only positive values of the integer, which meant that we were having a rotation clockwise around the circle viewed from below. So this is the physics convention for angular momentum. Whichever way you look at it, it's not terribly important. But my point is that you can go in both directions. So we could have written the formula J is equal to minus m over h. So rather than write plus or minus n in front here, we're going to write it like this, that say angular momentum about the z-axis The z-axis is the one perpendicular because our particle is in the xy plane. The angular momentum about the z-axis will be defined as a integer, m sub l, times h bar, and we will say m sub l will be 0, plus or minus 1, plus or minus 2, and so on. If this isn't already making a connection for you to freshman chemistry, in freshman chemistry, if you talked about an electron in a 2p orbital, the 2 meant that the principal quantum number was 2. N was equal to 2 for atoms. P meant that the angular momentum quantum number was 1. So that we use a symbol L was equal to 1. And then m sub L could range from plus 1 down to minus 1 and be plus 1, 0, or minus 1. So I'll connect this some more to what we have in atoms when we talk about the three-dimensional case. But right here, for this simple problem, I want to call this m sub L, so we'll be able to relate it later back to atomic structures. Okay, so this is no different from what we had before. Before I had E was equal to n squared times this business here. Now just change the quantum number to m sub L, but also pointed out that m sub L can be either positive or negative. And notice, so the energy is going to be independent of the direction of the motion because the square of a positive or negative number still comes out to be positive. Okay, well, the reason I like this problem is because we can also solve it by Schrodinger. Okay, James is way ahead of us, wondering about the Pali exclusion principle, and we will come back to that. And he's mentioned the very simple form of it, and we're going to see there's a much more complicated form of the Pali exclusion principle, maybe not this week, but by Monday or Wednesday of next week, we'll talk about how Wolfgang Pauli came along with his stuff. All right, so the reason I like this problem is because we can also do it by Schrodinger. The previous example, we just needed de Broglie and common sense, but now we can do the Schrodinger equation. So for the Schrodinger equation, sort of unfortunately, we have to use polar coordinates because we're going to have a fixed r, and if we try to work with x and y, it would get messy. So remember, we have the relation x is equal to r cosine phi, y is equal to r sine phi, and so here's going to be our problem. We're going to just have the angle phi telling us how far along the circle the particle is rotating. So in effect, we're going to have a fixed star, and we'll have a one-dimensional Schrodinger equation that we have to solve. Okay, so as I said, radius is fixed, so the energy and psi are not going to depend on r. The wave function will depend only on the angle of rotation phi that we have. If you go back to page QM-13, you will see I have the three-dimensional form of the Schrodinger equation where we use r, theta, and phi. I have reduced that problem to this by realizing that r is fixed, so we don't need any ddr terms. And I have also thrown out theta from the problem because we're only in a two-dimensional plane. So if it bothers you why we have this formula right here, go back to QM13, convince yourself that this is what we would have for fixed r and theta being our coordinate. Okay, well, again, I'm not going to make you solve equations of this type, but I will give you the result and the answer. The answer comes out that the wave equation is equal to a normalization constant times e to the imaginary I times m sub L times phi. And notice I have m sub L in this formula again. And here's an exercise, and I encourage you to do at home. Plug this into the Schrodinger equation, and you'll see this is exactly the result that you will get before. Okay, so as I said, this is why I like the problem, because you can get the answer two ways. A little warning that I put in brackets, the m here is mass, but in my formula, I also have m sub L, which is a quantum number. So I'm just following convention. I'm sure you saw this in physics a lot. We have the constant K used for umpteen thousand things. We've used it for a force constant. It can be a kinetic rate constant. Lots of things. C is used for many, many things. M here, unfortunately, shows up in two different places. Okay, notice that when we did the de Broglie relationship, we had a boundary condition that the wave had to match up on itself. For the Schrodinger equation, we can specifically and mathematically write the boundary condition, say that the wave function psi has to equal psi, the wave function at psi plus 2 pi. In other words, if we take the wave function at any angle and we go again a whole 360 degrees around the circle, that wave is going to have to be the same. Otherwise, this wave function would be destroying itself. Now, I could have also written phi plus 4 pi or 6 pi or 8 pi, but anytime we go all the way around the circle, the wave function has to match itself. And what I want to do here is use this boundary condition to learn a little bit more about what m sub L is. And so that's what I'm going to do on the next page. Okay, so psi of phi is equal to this. Psi of phi plus 2 pi will look the same, except I replace phi by phi plus 2 pi. You all remember, of course, when you have a sum in the exponents, you can write it as a product of exponential terms. So I have e to the iml phi for one exponent, and then the other exponent comes out to be e to the 2 pi iml. So these are the two terms we have. Our normalization constants cancel out, and you'll notice that e to the iml phi here will cancel out. So we're just left with the relationship that the exponential term has to be equal to 1. So this defines and dictates what the quantum number m sub L has to be. We go back to Euler, and all of you told me you've seen Euler umpteen thousand times. So if this is not as much magic to you as it is for my chemistry majors and biochemistry majors. So the exponential term with the imaginary number in there can be related to this. So this means, according to the substitution here, according to Euler, cosine of 2 pi ml plus I sine of 2 pi ml has to equal to 1. Now, the only way this can happen is if the sine term goes to 0, because we can't have an imaginary term in the result, and the cosine term has to go to 1. So luckily, whenever m sub L is an integer, we will have sine of 2 pi, 4 pi, 6 pi, 8 pi, anything else like that, or even sine of 0 works. So that works for m sub L being an integer. And also notice that the cosine of 2 pi times an integer will always be 1. Again, it could be 0, it could be 2 pi, in other words, 360 degrees, and the cosine is back to 1. So what this proves, according to Schrodinger, is what we also saw from de Broglie. M sub L is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, all the way up. Again, we will see these as showing up in atomic quantum states, and these are the angular momentum components in a particular orbital. So s orbitals won't have any angular momentum, and so p orbitals will have components m sub L equal plus 1, 0, and minus 1, and the angular momentum quantum number of L equal to 0. But again, I'll remind you of that later. Okay, so now I have good news and bad news for you. The next 3 or 4 pages in the notes are probably the worst and hardest to comprehend. And I used to spend 2 or 3 lectures on this. But when we had real classes and I could look into the students' eyes and everybody would get glassy-eyed as I talked about this, I decided to just condense this into the 2 or 3 pages that I'm going to show you. So that's the good news. We're just going to look superficially at our results. We have to look at it because we couldn't really talk about atomic structure fully if we didn't do that. So this will be a condensed version of what uh, we have to understand about atomic properties. So again, I'm going to take a little bit of a artificial problem, but we will go to 3 dimensions and we will have a particle like an electron. You can assume it's going to have a center that's going to be a nucleus, but to make the problem more understandable and more easily soluble, we're going to fix the R again. So R will be fixed, but theta and phi are going to be variables. So again, if you go back to page QM13, we have to go back to the Schrodinger equation in spherical coordinates in R, theta, and phi. When you solve it, these are the answers you get. You get energy levels in terms of the angular momentum quantum number. This is not an E. I kind of draw it sloppily, but this is a script L. If I try to do a lowercase l, it's going to look like a 1. But the energy levels are given by this angular momentum quantum number, also called the azimuthal quantum number. So this is just one of the results. L can be 0, 1, 2, etc. L0 will mean in atoms it's an s orbital, L1 is a p orbital, L2 is a d orbital, L3 is an f orbital, L4 is a g orbital, and so on. These solutions have complementary wave functions, as all Schrodinger solutions do. And they're given by spherical harmonics, and your text will talk some about these, and I think show you some of these. I'm just going to show you these 2 results right now. We don't need to look at them in much detail right now. But the wave functions are going to depend on 2 quantum numbers, this L quantum number, and then the m sub L that we just talked about for rotation in the z directions. So a couple of examples, L equal to 0, m sub L 0, that means no rotation. So there's no angular dependence. We just wind up with a normalization constant. If we wind up going to what would be a d orbital, we can pick an m sub L equal to +1. We would write the wave function as psi 2, 1. First subscript corresponding to L, the second one corresponding to m sub L. We would have a fancy normalization constant, then we would have theta dependence, and then we would have imaginary phi dependence. So life starts to get rather more miserable and unpleasant if we start wanting to work with this. Comment 3 is the overall angular momentum is going to be J is equal to square root of this, L times L plus 1 times H bar. Okay, so we can accept that. D is rather more complicated to understand. This is looking again at the 2-dimensional rotation we had. You remember we had the particle rotating in a circle about one direction. So when you go to a 3-dimensional problem, there's going to be a unique axis, which we're going to call Z, and we can look at rotation about that. And just as we saw a couple of pages ago, these energy levels are m sub L times H bar. Someone will inevitably ask what is a unique direction in an atom? Well, we scientists or engineers want to look at something in an experiment, we usually have to do something like apply a field to the atom. So we're always going to have a direction for an applied electric field or whatever we're doing. And so that's generally going to be our z direction that we look at. So one direction in a three-dimensional system, when we're doing experiments on it, is going to be unique. All right, so we're going to know what Jz is, and we're going to know how J, the overall angular momentum, is related to the components, and it's given by this formula here. The sum of the squares of the components is equal to the square of the overall angular momentum. So J squared total is equal to JC squared plus JX squared plus JY squared. We are never going to know individually what JX and JY are. We're just going to know what their sum is by being able to subtract JZ from J squared. So you can blame Heisenberg for this, or other wave properties, but this is one of the features of what we can know about these systems. Okay, so I've now repeated this many times, but this is what hopefully relates this to atomic systems for you. L0 means an s orbital, and m sub l is 0. L equal to 1 is a p orbital. M sub l can be 1, plus 1, 0, or minus 1. L equal to 2 would be a d orbital. M sub l can go from minus 2 up to plus 2. And if you've forgotten, this is why there are 3 orbitals in a set of p orbitals. You're talking about, say, the 2p orbitals. There are 3 of those. If you're talking about the 3 d orbitals, there are 5 of those. That's because we can have these different quantum numbers for each of those orbitals. I don't know if you spread that out in freshman chemistry when you talked about it, but this is where these numbers come from. Okay, I'll come back to some of this in a little bit, but I skipped over a page that I meant to tell you about after we finished the harmonic oscillator. But I wanted to give you an idea about why the Heisenberg uncertainty principle has the kind of magnitude that it has. Last time I gave you a definition for standard deviation. I first defined the variance. The variance was this expression for x without the square root. And then the variance was the standard deviation squared. So I'm now going to look again at the harmonic oscillator and the standard deviation. This is the definition that we have. But we can now look at the solutions we had and see what we get. We already went through solving this integral for what the average value of x was. So the average value of x squared we saw came out to be 0. And this is because we had an odd integral when we went from minus infinity to plus infinity. The x squared problem I didn't solve in your lecture notes, but it's solved in the practice problems that I've stuck into your notes. And this is the answer that we get before. Oh, sorry. No, this I did do in the notes, and we solved this before. We saw that this was an even integral, so we could take this to be 2 times the integral from 0 to infinity. We got the result. And so this was the result for x squared bar. So we now know what sigma x is for the harmonic oscillator. We also did the momentum problem, and not surprisingly, we got the average momentum was 0 because half the time the particle is going to the right in the plus x direction, half the time it's going in the minus x direction. So px, the average value of that, came out to be 0. The px squared, the average of that, is what I have in your lecture notes, and this is the result that you get. So again, the momentum, whether it be in the plus or x direction or the minus x direction, it will always have its square be a positive value. And so this will now be the average of that positive value. Okay, so this comes out looking like that. If we do the standard deviation for px, then it would be the square root of this expression right here. And so this is our result, looking just like this. And notice we wind up getting things to the 1/4 power. And here again is I'm repeating what the result is for sigma x. We have to take the square root of what we have here. Okay, so having gone through these definitions of standard deviation and averages and probability and so on, let's take the product of the standard deviation of sigma x times sigma px. We can write it as delta x delta px, and you'll see this is h bar over 2. You remember the Heisenberg uncertainty principle says the uncertainty needs to be greater than h bar over 2. So this doesn't prove the Heisenberg uncertainty principle. He would turn over in his grave if I claimed this. He took many, many pages in a physics journal to prove his relationships. But it kind of shows why we expect to get the magnitude that we do when we are looking, for example, here at the at the harmonic oscillator problem that we have. Okay, so nobody chatted or questions about that. We've just done the three-dimensional rotation. And now we come to another really, really weird thing in quantum mechanics. And it took years for people to believe this. Did I mention it? Yeah. Stern and Gerlach came along, and I maybe won't have time today to dig up the picture of the experiment, but they confirmed that this is what really happens for atoms in applied fields. But this is called space quantization. And be prepared for something weird. Hopefully you've gathered enough from what I've said on the previous pages that you don't mind my telling you again that J, the overall angular momentum, is quantized, and Jz, the angular momentum only in a specific direction, is quantized. Since this is the case, we wind up getting what's called space quantization. And this is going to mean that we can only have certain orientations of the rotations. So in effect, what we're saying is if we have an atomic nucleus and we're going to put an electron around it and it's going to have angular momentum, it can't whiz along everywhere it wants to. It's going to have to do it in certain orientations. Whenever the z direction is defined as it would be when we apply a field on this atomic system. Okay, so let's look to see how it works. For any value of the angular momentum quantum number, here's the overall angular momentum. J is equal to this. So just to relate what we're going to do down below, I'm going to pick L equal to 2. So this will tell us that the overall angular momentum is 2 times 3, the square root of that. So it comes out to be the square root of 6 times h bar. So this will be our overall angular momentum. The quantum numbers m sub L can be minus L plus 1 all the way up to L. For the L equal 2 case, it means m sub L can be minus 2, minus 1, 0, plus 1, plus 2. So the direction of the m sub L vector has to be such that the Jz components are given by this formula here. Remember that the angular moment Jz is m sub L times h bar. Okay, so I've drawn pictures here. Our overall angular momentum vector is 2. But if we put in, let me make sure I'm getting this right. Okay, square root of 6, okay, somehow I'm having a problem here. Square root of 6 is 2.45. Okay, so in the z direction, the overall angular momentum as a maximum can only be 2, but the length of this vector is 2.45. So I probably should have started here. Let's put the vector totally sideways from jz. And so it's going to have 0 component in the z direction. But the length of this vector defining the overall angular momentum is 2.45. So from here to here, the distance is 2.45. It says m sub L is equal to plus 2, but its actual length is 2.45. So the component along the z-axis has to only come out to be 2. So 2 represents the distance from the point here in the middle of the circle up to there. So it's a distance of 2. So I can't put this vector exactly along the z direction. I have to shorten it by creating an angle that's in there. Hannah asks, are we able to determine the regions of highest probability? It's worse than that. It specifically says this is exactly the component we can have. So the vector has to point exactly in this direction, but then the electron or whatever we have can only go around in this particular circle. So it can't, well, this is one of 5 options we have corresponding to the different 5 quantum numbers for m sub L. All right, so magnitude 2.45, by putting an angle in here, we reduce the component in the z direction to 2. We can also reduce it to 1 by putting an even lower angle along the direction here. And so this component has to come out, so it's ml equal to plus 1, or a magnitude of just of plus h bar. We talked about the 0 case when it's exactly sideways. It corresponds to m sub L 0. If we want to go and have the component be minus, then we have to start having the angle go below 0 here. And so we get a minus 1 component. And finally, we can get a minus 2 component. So you saw me stumble over my square roots of 6, and so I'm getting 2.45. The key point here is the vector is longer than the z components can be, and the z components have to correspond only to those 5 values. And by picking the correct angles that give you these things, then we're limited to only these 5 orientations of the angular momentum. I don't think I assigned a problem in your textbook, but there probably is one asking you to figure out what angles would be appropriate for d orbitals or p orbitals and so on. S orbitals you wouldn't have to worry about because there is no angular momentum. Okay, well, I think I've killed enough of the time. I'll try to remember to show you a picture of what the Stern-Jolla experiment looked like. They actually take a beam of and put it through an applied field, and then they look at the orientations that come out. I think they do this for silver atoms, but I'll confirm that next time. Okay, so the good news, oh, I'm sorry, I have it right here. So let's take the time and do it. I thought I had to go to a special slide like I had to do in past years. So I've stuck in this notes. So silver atoms travel through an inhomogeneous magnetic field and are deflected up or down depending on their spin. And this is what is observed. So they start from here. This is some kind of oven. They go through here, and we get those 2 points. If we understood silver atoms and what Stern and Gerloff did, we would understand it. The expected result is shown in 4. If there had not been a space quantization, then we could have had all angles showing up at this point, but we only got 2 specific angles in this particular experiment. Okay, well, we aren't quite done with the nasty part. I think we just have this 1 page, and so we'll finish that up on Friday, and then we'll actually be able to move on and talk about a real system, the hydrogen atom. Okay, any questions? Someone privately sent me a file. I don't know if I'm supposed to open it, but if you want me to respond to it, it'd be best to send it to me in an email. Okay, have a good rest of the week.